Hello everyone, all my dear students. In our previous video lecture, we had seen the examples of the sequential logic circuit and the combinational logic circuit. After that, we had seen the 1-bit memory cell. Now, we have to see the flip-flop and here various types of the flip-flop. For now here in this video lecture, we are going to see the construction and working of RS flip-flop by using the NOR gate as well as by using the NAND gate with the help of the logic diagram and its truth table. So let's go on the screen and see how the flip-flop works. If you will understand the video lecture, then hit the like button, subscribe the channel. The flip-flop is one type of a multi-vibrator having the two stable state. That multi-vibrator is we call as the bistable multi-vibrator. Here the bistable multi-vibrator having the two stable state, either it is high state or it is low state. So flip-flop is also having high state or the low state, and which state is high, which state is low after application of the input, that we have to see here. So the flip-flops basics we had seen already. The 1-bit memory cell. Now we draw the symbolical representation of the RS flip-flop and then we draw it by using the NOR gate and the NAND gate. Okay, so here I am going to draw a symbol for the flip-flop. Here the flip-flop having the two inputs. The two inputs are the R input and the S input. Here I am going to show the two input. One input is the R input and second input is the S input. Here it is S and the R. We can interchange the input and the output. So here the two outputs are there. These two outputs are Q and the Q bar. The two inputs are there. Here we can interchange the input. It may be S and it may be R. Here it is S and this one is the R. Okay. Inside this we write down the RSFF means the flip-flop. This is a symbol which we use for the representation of the RS flip-flop. Now here we have to consider the two conditions of the flip-flop. The flip-flop is either in the set condition or it is in the reset condition. When the flip-flop is in the set condition, it means the output Q is equals to 1 and Q bar is equals to 0. When the flip-flop is in reset condition, here the Q is equals to 0 and Q bar is equals to 1. Okay, so how we get the flip-flop is in set condition and in reset condition, that we have to see by using the logical diagram. But before going towards the logical diagram, I think we must know the working of the logical statement truth table and the working of both the gates, the NOR gate and the NAND gate. Okay, so we consider first the NOR gate. This NOR gate is constructed by using one NOT gate and one OR gate. So it is a combination of the NOT and the OR gate. The inputs are applied to the OR gate and the output of the OR gate is applied to the NOT gate, and here the output we get, that output is Y equals to A plus B complement. Okay, so we have to see the truth table of the NOR gate and the symbol of the NOR gate for the don't care condition. Equation of the NOR gate is Y equals to A plus B complement. Here in truth table we put A and the B input and the output is the Y. A0, B0, then we get the output Y is equals to 1. Why the output Y is equals to 1? 0 plus 0 is equals to 0 and its complement is equals to 1. So we get here output Y is equals to 1. If we consider the second condition, it is A0, B is 1, then we get its output 0 plus 1 is equals to 1 and its complement is equals to 0. When A is 1, B is 0, at that time again we get the output is equals to 0, and when A is 1, B is 1, here we get the output is equals to 0. By using these three conditions, we can say the output of NOR gate Y is equals to 0 or low when either A is equals to 1, either A is equals to 1 or B is equals to 1. Either A is equals to 1 or B is equals to 1, then the output of the NOR gate is equals to 0. Here we can write down the don't care condition of the NOR gate. Here if the NOR gate having many number of inputs, here for flip-flop we have to use either the 2 input NOR gate or the 3 input NOR gate. We consider only the 2 input NOR gate, and here if A is equals to 1, if the A is equals to 1, whatever the value of B, either it is 0 or equals to 1, then we get the output is equals to low, output is 0. It means that if any one input is high, the output of the NOR gate is equals to low. Don't care about any other inputs. Suppose B is equals to 1. If A is either equals to 0 or it is equals to 1, we get the output. That output is the low output. NOR gate is constructed by using one OR gate. So first we draw here the OR gate and the NOT is replaced by using the bubble. So here the 2 or more inputs are there. This is a symbol for the NOR gate. Here input is A and B, output is Y, and Y equals to A plus B complement, A plus B whole complement. Okay, so this is the NOR gate which we have to use in the flip-flop. The second gate is there, and that second gate is the NAND gate. We require to use the NAND gate for the construction of the flip-flop. So the NAND gate is constructed by using one NOT gate and one AND gate. The equation of the NAND is Y equals to A dot B complement. We can read it as A and B complement, or we can read it as A NAND B. Okay, so here the equation is A dot B complement. If we draw its truth table, then we get its logical statement or the don't care condition. If A is 0, B is 0, 0.0 is equals to 0, and the output Y is equals to 1 because Y is the complement. So here the A is equals to 0, B is equals to 1, 0.1 is equals to 0, its complement is equals to 1. If A is equals to 1, B is equals to 0, then we again get the output Y is equals to 1. And if both are 1, 1, A is 1, B is 1, then we get its output is equals to 0. By using these three conditions, first three conditions, we can define the NAND gate as the NAND gate produces logically high output. The NAND gate produces logically high output when any one input is logically low. Any one input is logically low or all inputs are logically low. The output of the NAND gate Y is equals to 1 when A is equals to 0 or B is equals to 0 or both A and B both are equals to 0. If we have to give the don't care condition, then here we can say that if A is equals to 0, whatever the value of B, here it may be equals to 0 or it may be equals to 1, output Y is equals to 1. If B is equals to 0, then output Y is equals to 1, whatever the value of A, don't care the other input. So here its output is equals to 1. Okay, now we have to draw the symbol of the NAND gate. The NAND gate is constructed by using the AND gate, and the output of AND gate is applied to the NOT gate. So here we apply the bubble at the output side, and here it may have the two inputs or more than two inputs. We consider only the two input NAND gate. So here A and B are the input and Y is the output, and Y is equals to A dot B complement. Okay, so the two things we have to keep in mind before going towards the working and the construction of the RS flip-flop. The RS flip-flop can be constructed by using the NOR gate and it can be constructed by using the NAND gate. Now we construct the NOR gate RS flip-flop, means we can construct the RS flip-flop by using NOR gate. The two NOR gates we require for the construction. I am going to draw here first the two NOR gates. Here is the first NOR gate. That first NOR gate having the output, and the second NOR gate is here. That second NOR gate is also having the output. That output we consider as a Q or the Q bar, depending on where we applied the inputs. One input of this NOR gate, is taken from the outside, and here one input is applied from the feedback, means output of one NOR gate is applied as an input to the second gate. Okay, so here the NOR gate symbol we drawn. The first NOR gate is having the two input, from that one is taken from the outside and one is taken internally. Internally means one is taken from the output side. Okay, so here the two gates are there. The output of the first gate is applied as an input to the second gate. Here I am going to apply the output of the first gate as input to the second gate. Then we apply the output of second gate as an input to the first gate. Okay, so this is the construction of the NOR gate. Here the two outputs are there. First output is here. That output is the Q output. I am going to use the different color so you can easily understand it. The output of this first gate, the upper gate is the Q, and output of the lower gate is the Q bar. The two inputs are there and the two outputs are there. Here the R and the S are the input, but here the two outputs required. The R and S inputs are the inputs of the NOR gate, but here we have to keep in mind which one is at the upper side having the Q output and which one is at the lower side having the Q bar output. So here this one, the upper one input is the R input. This is the R input and this one is the S input. So according to the sequence of the input and output, we have to make the construction. We can interchange it. If here the R is the input at the lower side, suppose here is the R input, then we have to apply here, we have to write down here the output. That output is the Q output. If here it is the S, then we write here the output. That output is the Q bar output. Okay, so the input to the upper NOR gate is the R and the output of the upper NOR gate is the Q. The input to the lower NOR gate is the S and the output to the lower NOR gate is the Q bar. Okay, so here we can write down the sequence, and that sequence is like this: R, Q and S, Q bar. Wherever you write down, at the upper side or at the lower side. If here the other flip-flop we consider, then the sequence may be different. Okay, so this is only for the RS flip-flop by using the NOR gate. Now we have to see the construction of the RS flip-flop and the working of the RS flip-flop by using the NOR gate. Here the two inputs are there and the two outputs are there. The inputs and the output sequence we had seen. Here we can say the output of the first NOR gate, that is Q, is applied as an input to the second NOR gate here. Means here the input is the Q and the output of the second NOR gate, that is the Q bar, is applied as an input to the first NOR gate. Means the output of one is applied to the second one as an input and output of the second one is applied as an input to the first one. Okay, so this is the sequence of the connections. Here we say it is the construction. Now we have to consider the working of this, how the flip-flop goes into the set condition and how the flip-flop goes into the reset condition. For that, here we'll give this, we apply the input with the sequence, and that sequence is again same 0 0 0 1 1 0 and the 1 1. Okay, so here we discuss first the application of the input and what type of the output we get, and at the same time we will write down the truth table. Okay, so here in truth table the inputs are the R input, then S input, outputs we again tabulate the Q and the Q bar output, and here we mention the condition of the flip-flop, and condition of the flip-flop means either the flip-flop is in the set condition or it is in the reset condition. Instead of the condition you can also write down the state of the flip-flop. Okay, so here the two inputs are there and the two outputs are there. These two inputs and the output we can apply, and here the input we apply, that input is in sequence. So first we apply the input, that input is R equals to 0 and S is equals to 0. R is equals to 0 and S is equals to 0. We consider here the initial state of the flip-flop to get the state of the flip-flop. So initially when we switch on the circuit, if this the output of this flip-flop is Q equals to 1 and Q bar is equals to 0, means the flip-flop initially is in the set condition, and we apply the input, that inputs are R equals to 0 and S is equals to 1. When R equals to 0, S is equals to 1, flip-flop is in set condition. It means here the Q is applied as an input to the second gate, and here for the second gate what we get here, 0 plus 1 is equals to 1 and its complement is equals to 0, means we get here the output Q bar is equals to 0. This Q bar is applied as an input to the upper gate, so the output of upper gate is Q and Q is equals to 1. Now the Q is equals to 1. After application of the input, R is equals to 0 and S is equals to 0. So here we can say there is a no change in the output of the flip-flop when we apply the input R equals to 0 and S is equals to 0. We consider the condition that initially before application of the input the flip-flop is in the set condition. Now we consider the flip-flop is in the reset condition and the inputs are not applied. Means here when we switch on the circuit, the inputs are not applied. The flip-flop is in the reset condition. It means the Q is equals to 0 and Q bar is equals to 1. Now we apply the input, that inputs are R is equals to 0 and S is also equals to 0. R is equals to 0. S is equals to 1, 0. Here the initially flip-flop is in the reset condition. Q is equals to 0, Q bar is equals to 1. It means here the Q bar is applied as an input to the upper gate and Q is applied as an input to the lower gate. Lower gate is having both the inputs are 0 0, so therefore here it produces the output which is equals to 1, and this Q bar is equals to 1 applied to the upper gate, so therefore here one input of the upper gate is equals to 1, so here its output is equals to 0. Means initially before application of any input, here the output of the flip-flop was in reset condition. After application of the input, again it retained the same state, it remains in the same condition, so we can say there is no change at all when we apply the input R equals to 0 and S is equals to 0. This condition is we call as the no change condition because it attempts the last state. Okay, so we tabulate the inputs in the truth table. So here R is equals to 0, S is equals to 0. Here we write down the last state. Here instead of Q equals to 0 or 1, we write down it is the last state, and here in condition we write down no change condition. Instead of no change, due to this small space here, I am going to write down NC. Okay, now we consider the second condition of the flip-flop. The second condition is when we apply the input R is equals to 0 and S is equals to 1. We are going to apply the input R is equals to 0 and S is equals to 1. For that, here we have to consider the don't care condition of the NOR gate. What we say in the NOR gate, if any one input is high, then its output is low. So here the S is equals to 1. It means here the output Q bar is equals to 0, and here Q bar is equals to 0. It is applied to the upper gate, so we get here both inputs are 0, 0. Its output is equals to 1. What we got here, when we apply the input R is equals to 0, S is equals to 1. Due to S equals to 1, here the output of the lower gate is equals to 0, and it is applied. The Q bar is applied as an input to the upper gate. Now, due to application of the Q bar, which is equals to 0, both the inputs of the upper gate are low. 0, 0, it produces the high output. Means we got here Q is equals to 1 and Q bar is equals to 0. But when R is equals to 0 and S is equals to 1, this condition of the flip-flop is we call as a set condition. This condition is we call a set condition. Now, here we apply the different input. That input is R equals to 1 and S is equals to 0. Now, R is equals to 1, S is equals to 0. It means the upper gate having the high input. So, therefore, here the output Q is equals to 0, and this Q is applied as an input to the second gate along with the S input. Both the inputs of the second gate, the lower gate, are low. So, therefore, it produces the output. That output is the high output. It means we get the Q is equals to 0 and Q bar is equals to 1. Here, this condition is we call as a reset condition. This condition of the flip-flop is we call a reset condition, and in reset condition we get the output Q bar is equals to 1 and Q is equals to 0 when R is equals to 1 and S is equals to 0. Okay, so this is the third condition of the flip-flop. Now the last condition we see when both the inputs are 1, 1. R is equals to 1, S is equals to 1. Here the output of both the gates tries to be equals to 0. Here the 0, 0 outputs are there theoretically, but practically it is not possible. Here we cannot define the state of the flip-flop. Either flip-flop is in set condition or in reset condition. But why we cannot define either it is in set or in reset condition? Here, as per the flip-flop theory, here Q and Q bar are always complement to each other. Here the Q is equals to 0 and Q bar is also equals to 0. There is a racing in between. The output Q and the Q bar. So therefore here we cannot define the output, and this condition is the invalid condition. This condition is we also called as the forbidden condition. This is the invalid because here in flip-flop theory what we required both the output Q and Q bar, whatever the output, either Q is equals to 1, Q bar is equals to 0, or Q is equals to 0, Q bar is equals to 1. Here the flip-flop output are always complement to each other. So therefore here this is the invalid condition, and we avoid to apply the R is equals to 1 and S is equals to 1 to the NOR gate RS flip-flop. Okay, so here we write down the same state when the R is equals to 1 and S is equals to 1. Here we get the question mark. We write down question mark because there is no define either Q is equals to 0 or Q bar is equals to 0. Either Q is equals to 1 or Q bar is equals to 1. And here this condition is we call as invalid condition. You can write down here the forbidden condition, or instead of the forbidden or invalid, you can also write down here the race condition of the flip-flop. Okay, so once again we recall the construction and working of the RS flip-flop in a very short. To construct the RS flip-flop, we require to use the two numbers of the NOR gate. The input to the upper NOR gate is the R input, and input to the lower NOR gate is the S input. The output of the upper NOR gate, that is Q, is applied as an input to the second NOR gate along with the S input, and output of the second NOR gate, that is Q bar, is applied as an input to the first NOR gate along with the R input. The flip-flop is having the two input R and the S input. Two outputs are there, Q and the Q bar output. Okay, so when we apply the input, R is equals to 0 and S is equals to 0, there is a no change condition. If the flip-flop was in the set condition, it remains in the set condition after application of the input. R is equals to 0 and S is equals to 0. When the flip-flop is in reset condition, it remains in the reset condition after application of the input. R and S both are equals to 0. Okay, now the second condition we consider when R is equals to 0 and S is equals to 1. When R is equals to 0, S is equals to 1, here we get the condition. That condition is the set condition where we get the Q is equals to 1 and Q bar is equals to 0. When R is equals to 1 and S is equals to 0, R is 1, S is 0. At that time here the flip-flop goes into the reset condition, producing the output Q is equals to 0 and Q bar is equals to 1. But when both inputs are 1, 1, at that time here we get the race condition or the invalid condition, because the output of both the NOR gate Q and Q bar are equals to same. So therefore here this is we call as the invalid condition. Okay, now we will see the construction and working of the RS flip-flop by using the NAND gate. Okay, so here we require to use the NAND gate and the two numbers of the NAND gate. Before going towards the working of the RS flip-flop NAND gate, here we recall the truth table of the NAND gate and the don't care condition of the NAND gate. So when both inputs are 0, 0, here its output is equals to 1, and when input A is equals to 0, B is equals to 1, again its output is equals to high. The A is equals to 1 and B is equals to 0, at that time again we get its output is equals to 1. It means if A is equals to 0, whatever the value of B, if A is equals to 0, whatever the value of B, the output Y is equals to 1. If the B is equals to 0, whatever the value of A, either it is equals to 1 or it is equals to 0, here we cross it and we get here the output is equals to 1. So we can say here the output of the NAND gate is logically high if its any one input is logically low. Don't care about the all other inputs. Okay, so we have to consider if input of the NAND gate is low, then its output is high. Okay, so we construct the RS flip-flop by using the NAND gate. Here for construction we required the two numbers of the NAND gate, and here I am going to draw the two NAND gate. Here it is the first NAND gate having the output. That output is again we consider Q output, and output of the second NAND gate is the Q bar. The outputs are the opposite outputs. The input to the first NAND gate is here the R input, and the input to the second NAND gate is the S input. The output of the first NAND gate is applied as an input to the second NAND gate, and the output of the second NAND gate is applied as an input to the first NAND gate. So I am going to apply here the output of the first one to the second gate and the output of the second gate to the first one along with the actual input. So here the input is the R input and here the input is the S input. So like the RS flip-flop using NOR gate, here also there is a construction, and according to this construction, here we can say the output of the first NAND gate is applied as an input to the second NAND gate. Here there is a connection. The output Q is applied as an input to the second NAND gate along with the S input, and output Q bar is applied as an input to the first NAND gate along with the R input. Okay, so once again we apply the input and find out the output condition of the flip-flop, and we tabulate in the truth table. Okay, so here in truth table what we required, in truth table we required the all inputs and their outputs. We required all inputs and their outputs. So here I am going to draw the truth table. In truth table we apply the inputs. Inputs are R input, then S input. The two outputs are there, Q and the Q bar. After that we write down here the condition of the flip-flop. That condition may be the set condition, or it may be a reset condition, or it may be the no change condition. Okay, so first we apply the input. That inputs are 0, 0. The input to the NOR gate are input to the NAND gate are R and S input, and that inputs are equals to 0, 0. R is 0 and S is equals to 0. Now when we apply the input, R is equals to 0, S is equals to 0. Here recall the don't care condition of the NAND gate. What we said just before, the NAND gate produces logically high output if its any one input is logically low. If its any one input is logically low, then its output is equals to 1. Means here theoretically we get Q is equals to 1 and Q bar is also equals to 1. As per the flip-flop theory, what we say, as per the flip-flop theory, we say the Q and Q bar are always complement to each other. The Q and Q bar are always complement to each other, and in this condition we get the Q is equals to 1 and Q bar is also equals to 1. So we said this condition in the previous flip-flop, that condition is the race condition. It is we call as a race condition because there is a racing in between the both NAND gate to produce the high output. It is we call as the invalid state because the Q and Q bar are same. We require the opposite output. Okay, so here this is also called as a forbidden condition. You can write down here R is 0, S is 0. The output Q having question mark, the Q bar is also having the question mark because we cannot define the output, and here we can say that condition is the invalid condition, or you can write down here the race condition, or you can write down here the forbidden condition. Okay, now we apply the other input, and the other inputs are R is equals to 0 and S is equals to 1. R is equals to 0, S is equals to 1. As per the don't care condition, if any one input of the NAND gate is logically low, then its output is logically high. So therefore here the input for the upper gate is equals to low, R is equals to 0. It means we get Q is equals to 1 and here Q bar is equals to 0. Why we get the Q bar is equals to 0? See here, the input to the second NAND gate, this one NAND gate is S, and S is equals to 1. Means one input of this second NAND gate is S, which is equals to 1, and second one input of this gate is equals to Q, and Q is also equals to 1. Both the inputs of this NAND gate are 1, 1. So therefore its output is equals to 0. It means here we get the Q bar output is equals to low. So here when R is equals to 0, S is equals to 1, here we get the Q is equals to 1 and Q bar is equals to 0. This condition is we call as a set condition. This condition is the set condition. Now we apply the different input. that input is the R is equals to 1 and S is equals to R is equals to 1 and S is equals to 0. When R is equals to 1, S is equals to 0, at that time the lower NAND gate is having the low input. It means here as per the don't care condition, it produces the output which is Q bar is equals to 1 and Q bar is applied as input to the upper gate. So therefore here both the inputs of the upper gate are 1 1. So its output becomes Q is equals to 0. Means when R is equals to 1, S is equals to 0, at that time the NAND gate flip-flop produces the output Q is equals to 0 and Q bar is equals to 1. This condition is we call as a reset condition. When the R is equals to 0 and S is equals to 1, at that time here we get the set condition. But when the R is equals to 1 and S is equals to 0, at that time we get here the reset condition. So here we write down R is 1, S is 0, Q is equals to 0 and Q bar is equals to 1. This condition of the flip-flop is we call as a reset condition, and in reset condition Q bar is equals to 1 whereas the Q is equals to 0. Now we apply the last condition here, last input condition. R is equals to 1 and S is equals to 0. R is equals to 1, S is equals to 0. It means here we have to consider the previous state of the flip-flop because we cannot produce the output by applying the R input and the S input. So for an example, suppose before applying the input R and S, the initial state of the flip-flop is in the set condition, means Q is equals to 1, Q bar is equals to 0. This Q is equals to 1, Q bar is equals to 0. Q is applied as input for the lower gate. So therefore here the lower gate produces the low output and this low output is applied as an input to the upper gate. So one input of the upper gate is low. It produces the high output. It means the flip-flop goes into the set condition, but actually it was in the set condition. After application of the input R is equals to 1 and S is equals to 1, it remains in the same state, means there is a no change condition. We can consider the other concept when this flip-flop is initially in the reset condition. Flip-flop is in reset condition, it means here the Q is equals to 0 and Q bar is equals to 1. When Q is equals to 0, Q bar is equals to 1. It means here the Q is applied as an input for the lower gate and Q bar is applied as an input for the upper gate. We consider here the Q bar is applied as an input for the upper gate. So the upper gate got both the inputs R and Q bar are 1 1. So it produces the low output and this low output is applied as an input to the lower gate. So therefore here the lower gate having the high output. It means here the flip-flop is in the reset condition. Actually the flip-flop was in the reset condition. It retained the same state. It remains in the same state. So here this is we call as a no change condition. So here we say when R is equals to 1, S is equals to 1, it produces the output. That output is the last state. Here we write down it is last state, and in condition we write down it is the no change condition. The condition is the no change condition. If we compare the truth table of the NAND gate flip-flop and the NOR gate flip-flop, both not having the same state, the two states are the different. For that here once again we go towards the NOR gate flip-flop truth table and the NAND gate flip-flop truth table. So this is the table of the NOR gate flip-flop. In NOR gate flip-flop we get here the when R is equals to 0, S is equals to 0, at that time the no change condition, and when R is equals to 1, S is equals to 1, there is a invalid condition. In the NAND gate flip-flop we get here the opposite state. When R is equals to 0, S is equals to 0, there is a invalid condition, and when R is equals to 1, S is equals to 1, there is a no change condition. Okay, so if we require the common truth table, the unique truth table for both of the flip-flop, then we require to change in the NAND gate flip-flop. So we draw the diagram for the NAND gate flip-flop with the change, means we apply the inverters at the input side. Therefore, that flip-flop is we also called as the S bar R bar flip-flop or the S R bar S bar flip-flop. Okay, so let's see the logic diagram of that flip-flop. So this is the logic diagram by using the RS flip-flop by using the NAND gate, but here we applied the two inverters, one inverter for the S input and one inverter for the R input. Here the outputs are same. The output of the upper NAND gate is Q and output of the lower NAND gate is the Q bar, but the inputs are interchanged with the S and the R input. At upper side, we had seen in previous logic diagram, here there is R input and here it is the Q. Here it is S input and here it is the Q bar. In NOR gate flip-flop also same, R and Q, S and the Q bar. But here in this case, by applying the inverters, we change the input, we interchange the input. Okay. So we apply the input and see what type of output we get after application of the input. So suppose here S is equals to 0, R is equals to 0 and here the inverter produces the output, that outputs are the 1 1. As we know, when the inputs to the NAND gate are 1 1, then it produces the no change condition, means there is a last state. But how we get the last state, that we have to see here. Now for an example, suppose before application of any input, here S and the R input, here suppose Q is equals to 0 and Q bar is equals to 1, means the flip-flop is in the reset condition. If we apply the input S is equals to 0, R is equals to 1, at that time here we get the upper inverter's output is equals to 1 and lower inverter's output is equals to 1. The upper inverter's output is applied as input to the upper NAND gate, this one, and the lower one inverter's output is applied to the lower gate. The output Q is again applied as the input for the lower gate, means here there is a Q and here the output Q bar is applied as input for the upper gate. So here the Q is equals to 0, it means one input of the lower NAND gate is 0, so therefore it produces the high output, means we get the Q bar is equals to 1. This Q bar 1 is applied as input to the upper gate, so therefore here we got here both the inputs are 1 1 of the upper NAND gate, so therefore it produces the low output, means here the NAND gate having the output Q is equals to 0, Q bar, the flip-flop having the output Q is equals to 0, Q bar is equals to 1. Before application of the input, it remains in the same state and producing the output Q is equals to 0, Q bar is equals to 1, means there is a no change condition. We also verify the same state if the flip-flop was in the set condition before application of the input. Suppose here before application of the input Q is equals to 1 and Q bar is equals to 0, means the flip-flop was in this set condition. Now we apply the input and inputs are S is equals to 0, R is also equals to 0. Here the inverter produces the output, that outputs are the 1 1 and these are applied to the NAND gate flip-flop. Okay, so Q is equals to 1, it is applied to the lower gate, so therefore here the lower gate produces the low output because both the inputs are 1 1 and the upper gate produces the high output. Why? Because one input of this gate is equals to 0, so therefore here we get the high output, means Q is equals to 1, Q bar is equals to 0, flip-flop is in the set condition. Before application of the input S and R both are 0 0, here it was in the set condition, now again it remains in the set condition, so there is a no change condition. In NOR gate flip-flop we get again the same state when S is equals to 0, R is equals to 1, R is equals to 0, the flip-flop attained the last state. I am going to write down here the last state and the condition is we call as a no change condition. In short, I am going to write down NC. Okay, now we apply the different input. The second combination is when S is equals to 0 and R is equals to 1. Here R is equals to 1. The S is equals to 0 means the upper inverter produces high output, whereas the lower inverter produces the low output. The lower NAND gate having the input that input is low, and here as the low input is there, it means the output of the lower NAND gate Q bar is equals to 1. The lower NAND gate output produces the Q bar equals to 1, and this Q bar is applied as an input here, means the upper NAND gate, this one NAND gate having the inputs are 1 1, so therefore it produces the output, that output is equals to 0, means when we apply S is equals to 0, R is equals to 1, we get S is equals to 0, R is equals to 1, we get Q is equals to 0, whereas the Q bar is equals to 1. This condition is we call as a reset condition. If we see in the NAND gate flip-flop, again there is a reset condition. When S is equals to 0, R is equals to 1, there is a reset condition. If we see the same state, when R is equals to 1 and S is equals to 0, there is a reset condition. Okay, so here we get the reset condition. When we apply the input, that inputs are S is equals to 1 and the R equals to 0. At that time, here there must be a set condition. We say how we get the set condition. Here S is equals to 1. It means the upper inverter produces the low output, whereas the lower inverter produces the high output. The upper inverter's low output is applied to the upper NAND gate, so therefore here the upper NAND gate produces high output, and this high output is fed back to the lower gate, so therefore here both the inputs of the lower gate are 1 1, so we get Q bar is equals to 0. It means when S is equals to 1, R is equals to 0, we get Q is equals to 1 and Q bar is equals to 0. This condition is we call as a set condition. Okay, we get the set condition in the NAND gate flip-flop, previous NAND gate flip-flop, as well as in the NOR gate flip-flop when S is equals to 1 and R is equals to 0. Now we apply S is equals to 1. We apply S is equals to 1 and R is equals to 1. Both the inverter produces the low output, means here input to the upper NAND gate and the lower NAND gate are 0 0, means one input of the upper NAND gate is 0, so it trying to produce the high output, as well as the lower NAND gate trying to produce the high output. There is a racing in between the upper and the lower NAND gate to produce the Q and Q bar to produce the high output. So therefore here we can say the output of the upper gate is and the lower gate is not defined, so there is a invalid condition. We get theoretically we get the output, that outputs are 1 1, and this is not in the flip-flop theory. What is in the flip-flop theory? We say the Q and Q bar are always complement to each other. So when S is equals to 1, R is equals to 1, here we can write down question mark, here again question mark, because we cannot define this state, and this state is we call as, this condition is we call as the invalid condition. If we say in the NAND gate flip-flop and the NOR gate flip-flop, we get the invalid condition. Here 1 1 input means the state is the invalid state. Okay, so we got here the unique table in between the NOR gate flip-flop and the NAND gate flip-flop. Okay, so here we once again recall the condition of the flip-flop by using the NAND gate and the NOR gate by applying the inputs to the symbolical representation, to the symbol of the NAND gate and the NOR gate normal flip-flop. Okay, so this is the symbol of the flip-flop, RS flip-flop, having the two inputs. Which are those input? S input and the R input. Here the two outputs are there. The two outputs are again same, Q and the Q bar output. Here the outputs are the Q and the Q bar, two outputs. When S is equals to 0, R is equals to 0, here there is a no change condition. Whatever the previous state of the flip-flop, it remains in the same state. That state is we call as a no change last state of the flip-flop. If the flip-flop is in the set condition before application of the input, it remains in the set condition. If it was in the reset condition, it remains in the reset condition after application of the input. S and R both are equals to 0, 0. When S is equals to 0 and R is equals to 1, at that time we get the Q is equals to 0, Q bar is equals to 1. This condition is we call as the reset condition. This condition is we call as a reset condition. When the S is equals to 1 and R is equals to 0, at that time we get here Q is equals to 1 and Q bar is equals to 0. This condition is we call as a set condition. This is the set condition of the flip-flop. When both are 1, 1, S is equals to 1, R is equals to 1, here we cannot define the state of the flip-flop. This condition is we call as the invalid condition. This condition is the invalid condition. This is not according to the flip-flop theory. Here, as per the flip-flop theory, the Q and the Q bar are always complement to each other. Okay, so this is all about the RS flip-flop by using the NOR gate and the RS flip-flop by using the NAND gate. Next time we will see the RS flip-flop using the clock. That flip-flop is we call as the clock RS flip-flop. If you understood this video lecture, then hit the like button and subscribe the channel. Thanks for watching the video. Take care.